Hi. Great to see everyone back again. Same time. Good to see you here. I'm just going to invite our speaker up again. Usual process. I'm sure you're all very familiar with how this works now. Once again, drop your hellos in the chat. Archie beat me to it. GM. Ben, back again. Great to see you. It's awesome to see so many of you. Hi, Zheng. How are you?
Hi there. Can everyone hear me?
Yes, I can hear you good.
Great.
Feel free whilst we're just getting set up. Maybe you want to just share your screen or your slides. But yeah, as I was saying, it's great to see so many of you coming for all of these sessions. I'm recognizing a lot of names and a lot of faces, so it's good to see you all coming back. I think you're arming yourself well for any projects that you're looking to build. So keep asking your questions live. It's always best to get all of the insights whilst we have the experts here delivering the workshop. So make sure you stay active and ask your questions whilst you're here. Again, as always, the sessions will be recorded. So if you're watching this on the recording, good to see you. Thank you for watching this back. But I think everyone is here. I'm sure some people will continue to load into the room as well. So it's 2 minutes past. Let's kick things off. So yeah, hello everyone. Great to see you all once again. Really excited today. We have Automata here to deliver our workshop, and specifically we have Zheng Leong. So yeah, really excited. I hope you all enjoy the sessions. Feel free to ask all your questions in the chat. Hopefully we'll have some time to cover those at the end. But otherwise, Zheng, I'd love to hand straight over to you to kick things off, if that's okay.
Yep, sure. Thanks for the introduction. So maybe I'll just skip the kind of like self-introduction. Just maybe a little bit about myself. I'm one of the co-founders for Automata Network, and I'm kind of like your average geek doing the things that an average geek love to do, which is to build, to hack, to build cool stuff. So I'm very kind of like happy to be invited today to share with all of you like uh, some kind of like insights or some experience that we have building like multi-prover AVSs using TEE coprocessors. So really, what's at stake with multi-prover AVS, if you kind of like get the pun. Anyway, jokes aside, let's move on proper. So sorry. Okay, so really, what is Automata Network, right? Automata Network is actually a modular attestation layer that extends machine trust to Ethereum with TEE coprocessors. So there's a lot of kind of like words here that some of you might not be familiar with. So let's kind of like break each of it down. Let's start off with TEE coprocessors. What are TEE coprocessors? You can think of them as like magical black boxes. Like there's this magical box that you can like open up, put things inside there, like your say your precious letter or like a recipe. And then when you close the box, there will be magical elves inside the box that will actually go and follow your recipe and maybe like bake you a cake from within this magic box. Now, the nice thing about this magical box is that no one can actually see what is happening inside there. So your secret recipe that makes the best cupcake in the world will actually be safe within that box. And similarly, no one can actually kind of like add weird things into your magical box. So if you have a recipe for a banana cupcake, you're going to get a banana cupcake. You're not going to get like chili flavored cupcake or like some weird flavors, right? So this is actually what this magical box allow you to do. And I'm kind of like using an analogy, but this is what TEE coprocessors give us. It enable us to like have confidential computation, verifiable computation within a CPU that is not under our control. So that is the thing about TEE coprocessors. What about attestation? Like, what the hell is attestation? Well, the thing about attestation is it's just a fancy word of saying like a proof or like verifying or making sure that something is indeed what it claims to be. So I'll give you some examples. For example, like your passport is actually a kind of like a proof that I am a particular citizen of a country, right? So what I can do is, if I want to know if you are, say, myself, I'm a Singaporean. If I am a Singaporean, then say Rory would perform an attestation on my citizenship. Then what I'll do is I will show Rory my passport. Like, this is the proof. Rory will take my passport, open it up, and see. Yeah, correct. Zheng Leong is indeed like. This is a real. This is a real passport issued by Singapore, and yeah, the person is indeed Zheng Leong. So yeah, he's a citizen in Singapore. So that's the idea of attestation. So from this kind of like these two kind of like key concept, what we really want to do here at Automata Network is to be able to let people, or at least let Web3 participants, have some sort of trust grounding on the actual silicon that they are running their computation on. They're storing their NFT on, they're doing their transactions on. So, you know, the thing about like our entire Web3 how to say ecosystem is that like trust no one, right? But trusting no one is such a tiring thing sometimes. Sometimes if we have the ability to, it would actually be better for us to kind of like extend our trust. Of course, that extension of trust must be validated. It must be earned, so to say. And this is the kind of like backdrop where we come in. So we want to actually build this attestation layer that kind of like, you can think of it as it's a layer above or under, depending on your perspective, that lives on top of the execution layer. So we know that we have the execution layer, like all our rollups. We have the settlement layer where all our security of the execution layer is based in. And what we want to do is build this attestation layer on top of it. This layer where you can verify entities and kind of like extend your trust to these entities. So that's what we do basically. So you might be thinking like, hey, so yeah, we have this attestation layer. So what are we going to do with it? Like, how can we extend this trust, right? So we came up with this concept called proof of machinehood. So what is proof of machinehood really? Like, wow, it's really such a fancy word. But you can think of it as basically this proof of machinehood is a passport for your machine. Like, each of your machine, especially machines nowadays, like your iPhone, like Apple is very proud to say that they have a secure enclave in each and every of their Apple devices, your MacBook Pro, your iPad, your iPhone. And you can think of this secure enclave as having this passport because it's unforgeable. It's made by Apple, it's issued by Apple. And then we can make use of this passport to actually verify that you are, say, sending an NFT from an authentic iPhone, or you're like claiming a particular NFT, minting an NFT from your MacBook Pro. So we call this proof or this like collateral, this item that lives in all your devices, a proof of machinehood. And what this allows us to do is this allows us to take this proof, put it on chain. People can then verify this proof and know that, hey, you're indeed running a genuine device. And the nice thing about this is this kind of, you can think of it as this proof of machinehood as being an NFT. So now I have an NFT, I have this passport that proves that my machine is genuine. Things like the apps can actually make use of this proof of machinehood to do many things, like assign you maybe certain NFTs, or like allow you to do certain operations, which I'll share a little bit later. So basically, this is like the proof of machinehood that lives that is basically the passport for devices in this attestation aligned world that we envision, that we hope we can live in. So I guess a very good way for you guys to kind of like experience this, what this proof of machinehood is via say a demo. So we actually have a demo of this POM. I have just typed the URL on the chat, pom.ata.network, where you can experience what doing device attestation would feel like. And we actually have a testnet that all this proof of machinehood would be verified on. And currently, at the moment, we have about 160,000 attestations. And this is on our L2 testnet. Now the thing is, if all this attestation is verified on the L1, because we always need to verify a proof, right? Like I said, this trust has to be earned, and you earn this trust by verifying the evidence. It will actually be about 900 ETH more expensive. So I think it's about $3 million. It's less than 3 million. It's about 3 million USD. So by actually moving this verification into a dedicated rollup, into a kind of like attestation layer, we can actually improve the efficiency, make it more accessible to all the developers and DApps by decreasing the cost, by allowing users to save the gas. That's if I'm not wrong, it's about 10. You will save about $20 US per verification, which is quite substantial. Can you imagine, like, if I want to do a transaction and it will cost more than $20? I mean, people wouldn't actually use it. So that is kind of like a key reason why we have this idea of attestation layer, where it focuses on that one goal of performing attestation verification for everyone. So let's take a look at. So now that we kind of like understand what attestation is about, what this attestation layer is about, and this this nice abstraction, this passport that we have, this proof of machinehood, what can we do about it, right? Here, I'll kind of like, I guess most of us here, we are actually like hackers, right? We develop, we are builders, we develop interesting applications. So I'll share two products that we developed at Automata that actually make use of this idea of attestation. So one of it is actually an attestation that the provider produced in order to prove to the user that it is indeed doing something. Now, the other product is actually an attestation that is produced by the user to prove to the provider that is doing something. So the two products in question is actually one RPC and L2 Fawcett. I'll kind of like share a little bit more what these products do, and I think it'll actually be useful for the hackathon that I guess you guys will be participating in. So one RPC is actually a privacy relay. Now the idea of it is that we actually took a proxy. We can think of it as an RPC proxy, and we run this RPC proxy within the TEE itself. So remember that the TEE is this magical black box. Now that we are actually running a proxy within this magical black box, we can no longer see what other kind of like content that is being processed within this black box. So what does one RPC do? It actually removes certain like sensitive, privacy sensitive metadata, like your IP address, your the extension that you use to actually send the transaction, which origin are you from, what is the browser that you're using. So all these are sensitive information that RPC providers can use to track you, and one RPC will actually remove it. Furthermore, you actually disassociate your IP address from the actual transactions that are being sent. We'll do like unbundling and then combining your transactions with other people's transactions before sending it out to all our data providers. So it's more than one data provider. So your data won't be actually sent to not all your transactions will be sent to a single RPC provider. So this kinds of like distributes the risk to multiple RPC endpoint. Now you might be saying, hey, like at this point, why should I use one RPC? You're just like any other RPC provider, right? You can see my stuff. This is where this attestation comes into play. So like I say, because we are running one RPC within the trusted execution environment, which is a magic black box, I can prove to you that I actually have a real magic black box, not a fake magic black box that you find in some random bazaar. Now, the way how I do it is I will create a attestation report. The user can take this attestation report and then send it onto our Automata L2 to get it verified. Or like what we are doing now is our proxies would actually take their report and post it onto our L2. So any user can just go to our L2 and look for the proof of machinehood to know that, hey, the proxy is indeed being attested, and the proof of it lives on our attestation layer. So one RPC is this example of a service where a provider makes use of this proof of machinehood to kind of like give confidence to the user. Now, the other way around, we have this service called L2 Faucet. I think as developers, it's very common for us to want to get like testnet tokens in order for us to deploy our contracts, interact with our DApps on testnet. And it's really troublesome to interact with testnet because there's some bridging involved for us to move the tokens from, say, Sepolia to, say, Scroll testnet or Optimism testnet. And then you would have to do things like, review yourself, dox yourself, share your social account, stuff like that. So what we built here is actually a service where instead of us saying that, hey, review yourself so that we know you are not like exploiting us and trying to drain our wallet, like our faucet wallet. Instead of doing that, what we are saying is that we will actually provide you a drip of the testnet tokens to a specific real device that you own. So for example, if you own a particular like iPhone or say a particular Android phone, then what we would do is for this Android phone, we will allow you to maybe receive 5 drips of testnet token every day. And the way how we know that you own a legitimate Android phone or a legitimate iPhone is again using attestation. So this time the user will prove to the provider, hey, dear provider, look, I have this phone. From the phone, I will generate this proof of machinehood, and then you can verify this proof of machinehood to know that I have a real phone. And after we verify this proof of machinehood, then we'll provide you with the testnet tokens. So these are like 2 examples on how attestation can actually be used in the real world to provide services to users. And we are actually very proud to say that we are probably the first to actually implement like a proxy and a faucet using this trusted execution environments with attestation. So I guess you guys will actually be working with a lot like cross-chain, multiple testnets. You guys will be hacking, and I hope that these 2 services will actually kind of like help the developers, like provide developers with the tools and resource to actually build the kind of like product or project that they really enjoy. So with that out of the way, right, like that's basically attestation and a little bit on TEEs. Then we really want to talk about like multi-provers for decentralized system, and like what are multi-provers and why do we need this whole multi-prover? Now, the current latest hottest thing in our entire ecosystem is ZK proofs, like ZK everything. There's ZKML, there's ZK rollout, and there is sorry, Rory. So do I answer the question now, or we'll address it at the end?
Yes, it's completely up to you. If you would rather attack it now, feel free to do so. But we should also have time at the end as well if you'd rather go over them then. But no, feel free to go ahead now if that works.
I see. So I'll kind of like touch on it a little bit. So the proof of this kind of phone is actually, it originates from that kind of like hardware root of trust that I talk about. So like I say, for example, for your iPhone, you have a secure enclave that is embedded in each of the Apple device. You can imagine, it's not directly that, but you can imagine that there is a secret key, there's a private key that Apple embeds in each of these devices. Now, what we can do is we can use this private key that's embedded in the device to actually sign a proof, and then we can verify that this proof actually originates from Apple. And that's how we can know that this is a genuine Apple device. Now, for custom device, it's a little bit more complicated. The device would need to have this hardware root of trust that I talk about, and then we need to have a way to establish the trust and the protocol involved in verifying this trust. So I hope I answered your question. So let's kind of like move on. So as I was saying, ZK is this latest hottest thing in that is happening. That we are basically ZK-ify everything in our Web3 ecosystem. Like we have ZKML, ZKAI, ZK rollups, ZKVM. That is like ZK for privacy transactions. Like if we can stick ZK in, we will put ZK. And it's not without a reason. ZKs are really, really powerful. It is like a correctness proof. It is able. It allows us to actually generate this proof that proves that something is actually correct, and that is actually a completeness and soundness proof. Like I prove that for all cases, like if in all cases that can happen in the whole world, this thing that I'm trying to tell you is indeed true. And this allows us to do a lot of fancy things. But herein lies the issue. ZK systems are extremely complex. There is a lot of very advanced math that is that is kind of like the cornerstone of ZK proofs. And ZK proofs are like really new to like we see projects that is announcing like new ZK what's it called, proving systems, schemes, new circuits that like improve the state of the art by 10 times, by 100 times. Like things are coming out fresh from the oven, and because of that, really, the entire environment is actually changing really rapidly, which leads to issues like lack of developer tools, really hard to use. There's not a lot of experts around that you can find to actually audit the correctness of some of the ZK components that we have. And because it's so new and so hard to develop for, a lot of rollups actually don't have like a kind of like complete ZK system. Or like actually nowadays we have like ZK EVM, which makes things a lot easier. It's a general system that allows us to perform computation. But like I said, what we are doing here is that we have this really awesome thing called ZK proofs. It is extremely powerful. It allows us to prove correctness, but it is extremely complicated, really hard to get right. There is a lack of tools to make it easier to code for. The math behind it is extremely complex, and we don't have a lot of people to actually audit and make sure that all this thing is correct. So what do we have? Bugs, and a lot of bugs. And if we have a proof that proves the correctness of something, and this proof has a bug, it actually means that I can kind of like I can create a proof to prove something that is actually wrong, and you would believe that it is correct. So what can we actually go about? What can we do to help make the situation better in this case, right? So this is where where the idea of multi-prover comes in, really. Like relying on a single proof system, like what ZK proof would kind of like have a single point of failure on the prover itself. So if there's anything wrong with the proof, everything fails. Now, what if we actually take this proof and then we kind of like we put what this proof is trying to do into that magical black box that I told you about? Now we have two proofs. We actually decentralize, we distribute the responsibility of proving into two separate proofs. And at this point, both need to agree before we say that, hey, the particular transaction that you want to do is correct, or the particular block that has been generated is correct. And this whole thing actually makes the whole system a lot more robust. So this is actually the importance of having a multi-prover. Then you might actually be asking like, hey, then why TE, right? So you'll recall what is the two properties that I've told you about. One of it is that this black box allows you to secretly to store your things without anyone peeping into it. What does the ZK proof does? It actually protects like your privacy, right? Your privacy is something that you might want to protect. This is exactly what TEEs can give you. What about the other one? ZK proofs are trying to like prove the correctness of something. Like I said, if you put a recipe within this black box, this black box would make sure that your the fairies inside this magical black box would make sure that your recipe is being followed to the letter. This proves the correctness of the code that I am trying to run. So TE actually very nicely provide these two kind of like properties that we want from ZK provers. And you know what is the best thing? It actually provides it at extremely low cost. It's extremely efficient and it's super easy to develop for TEs. It's just like writing a normal program instead of trying to like figuring out how Halo 2 works, coming up with that matrix, that table of like matrices to make the circuits actually come together. So these are some of the benefits of having this TE prover. So I'll kind of like skip this quick LE5 on TEs. I actually have a blog post on TEs. If you guys are interested, I'll just share a link there and then you can go take a look. But I guess you can think of it as this black box that runs stuff, and you can be sure about like privacy and integrity of your computation that is executing within. Of course, all this is under the assumption that you trust the black box. So specifically for the TE prover, we actually have a particular implementation. We adopted Intel SGX. You might be thinking like, hey, Intel SGX, isn't it that thing that keeps on getting broken? Well, I would like to say that I contributed to some of it. I actually wrote a paper that broke Intel SGX. But that aside, I'm here telling you that although I broke Intel SGX, it's actually not that bad. The thing is, there are always ways to mitigate some of the problems with Intel SGX and some of this TE that we are using. So we would want to use it in a manner where you would mitigate away some of the kind of like issues that this kind of TE environments actually bring about. So yeah, that's kind of like the reason why we use Intel SGX. And to kind of like share a little bit, in order to lower the kind of like computation footprint and to minimize the amount, the trusted computing base. So it's like we don't want to put the whole kitchen inside this magic box, right? We just run the recipe inside the magic box. The rest of the kitchen can actually be outside. The most important thing is the recipe. So we actually we don't use the grounding framework to actually build this TE prover. We actually build it from scratch, ground up, using the Intel SGX SDK, specifically the Rust Intel SGX SDK. Now, I think I've actually kind of like touched a little bit on this. What this allows us to do is to have verifiable trust and practical overheads, basically low overheads, it doesn't take like a whole server farm to compute the trust. The latency between it is actually a lot lower. So to kind of like to go deeper in, we actually built a TEE prover with Scroll. The code is actually open source. The what's it called? The GitHub repo is now shared on screen. Automata Network /SGX prover. So for this particular TEE multi-prover, we actually use Sputnik VM as the EVM interpreter. This Sputnik VM this Sputnik VM is actually a pure Rust implementation, and it has support for no STD, like no standard. You can think of it as a freestanding binary. So you can kind of like run it within SGX or run it in a normal environment, it will work. So since our binary, our TEE prover can actually run in both like SGX and non-SGX environments, we actually did a benchmark for it. And what we realized is that there is there's about 10%, less than 10% performance loss in terms of the SGX. That means all the encryption and the context switches that goes behind the scenes. In total, there's less than 10% performance loss. So it is actually extremely feasible. I mean, if you compare that to like ZK circuits, right, where you get like, I don't know, like maybe 1,000, like 100 times or 1,000 times more computation to do like slower. This is extremely usable. So currently we have actually used this TEE SGX prover on both the testnet and mainnet, and we are following Scroll's what's called published blocks on both testnet and mainnet, and up till now they concur. So if they disagree, there'll be something interesting that we can talk about. But at the time being, it's actually the same. Now, there's an interesting thing. One interesting thing is that Scroll actually recently changed their, actually implemented this REVM version of their Scroll client. So what we do is we actually took it and then we put it into our TEE, and then we actually use it to follow the mainnet, the Scroll's mainnet, and we actually found some implementation bug with regards to the REVM. That Scroll did. Of course, we told them about it and they have fixed it already. So like this is something that is super useful, you know, having this multi-prover that would check each other. The ZK proof can check the multi-prover, like the client that you're using. The client can check the ZK proof circuits. So it's kind of like a win-win situation. So other than Scroll, we actually also have a linear implementation. So the linear implementation, so just to share a little bit, the Scroll implementation is currently live on our AVS. So all our AVS operators are actually it's actually helping Scroll in making sure that their proofs are correct and that the client implementation within the multi-prover is actually correct. So we have completed the implementation for linear. It will actually be online during the next like V2 of our AVS. So look out for it. And currently this link is actually not accessible, but we actually have the R0VM made into a multi-prover tool. We are kind of like cleaning up the code. We'll be open sourcing the code soon. So since we are on this topic of open source, right, I would also like to share our kind of like Intel SGX DCAP attestation contract. So if you guys are interested in doing like Intel SGX enclave and you want to be able to attest your enclave, you can use our Solidity contracts. It's open source now, or you can directly use our L2 that I have kind of like shared with you earlier on. Okay, so now that we have talked about like, you know, attestation, TEs, like proof of machinehood, trust, and you know the yummy thing about like multi-provers and why multi-provers are so important. You might be asking like, yeah, great. Now we have this multi-prover thing. Why do we need EigenLayer? Why do we need an AVS? Can't we just run the multi-prover? Doesn't it work that way? So here I'm hoping that I can kind of like share with you some of the insights that we have in how the crypto economic security that AVS brings to the table that is provided by EigenLayer actually helps augments whatever guarantees that our TEE multi-prover actually provides. You can think of it as, hey, you can think of it as the kind of like crypto economic security as being an insurance for your multi-prover, for your TEE multi-prover. Now, the thing about this is that it's great that we have this really fancy technology, this TEE that allow us to guarantee correctness and privacy, right? But the thing is, the operator can just take a scissors or take a knife and like cut the network cable or like pull out the power cable, and then the machine will go offline. So we can protect against correctness, against privacy, but we can't TEs can't actually protect against liveness, or can't to a certain extent. In this case, the economic bond that is provided by EigenLayer, the crypto economic security, would help greatly in this, because this crypto economic security actually disincentivize the operators in in having a situation where their TEE is offline. So it actually incentivizes them to make sure that their TEE is online, because it's the opposite thing, right? So you think of it, now we have a model where we have TEE that gives a guarantee on or confidence on like correct execution and privacy, which means that it's actually very hard, if not impossible, for someone malicious to actually send something bad. And on top of it, you have an additional insurance to make it such that if you actually do something bad, you need to pay the price of doing that bad thing. So it makes something that is already hard to do even harder. And this thing, like, we always like to have security, kind of like layers of security to make things better, right? Like defense in depth, that's the kind of like term that we use in the security space. So that is on the kind of like the security side that AVS is bringing us. But now that we actually have this crypto economic security, this kind of insurance, we can there's actually more things that we can do with our multi-prover now. So imagine that we are running, say a ZK rollup. A ZK rollup, each rollup for the ZK rollup would take like, I don't know, 5 minutes, 10 minutes for the proof to actually be batched, and then they have to send it to this really big server farm to generate the proofs for it, and then the proof finally being sent on chain. So there's actually this latency between like when a block is generated to the block finally being verified on the L1. In certain cases, like in like crypto games, this kind of 10-minute lag between each action is unacceptable. It's just purely unacceptable. So what we can do is we can actually make use of the TEE, now that is backed by an AVS with the crypto economic security. We can use the TEE to provide extremely low latency roll-ups onto the base layer, because it's nearly like free. It's nearly free for the TEE to actually verify something. It's just the cost of performing the execution again, and then the TEE would sign over it and then send the transaction out. And this and all of this like optimistic attestation that's being put on chain, or this kind of like TEE attestation can then be verified in a single block by the supposedly more secure but slower ZK proof. So you get the best of both worlds. You get good latency, and you have you ultimately have like an arbiter, a judge to protect you against any black swan event that might occur, such that the TEE actually produces a bad result. And all of this is enabled through this crypto economic security that AVSs bring to the table. And finally, I've seen a question in the chat that kind of like asked this question about, hey, if you are relying on Apple's device signatures, right, then how do we maintain this decentralized aspect of things? Like, because we are relying on Apple, right? You're totally right. So if, for example, when we make use of Intel SGX, we are relying on Intel to provide this root of trust. But the thing is, Intel is not the only vendor that provides this trusted execution environment. We have Amazon with their Amazon Nitro Enclave. We have NVIDIA with their new confidential GPUs. We have ARM with their Trust Zone. We have AMD with their AMD SCV TEs, their EPIC CPUs actually have this option. There are even like RISC-V TEs that are being developed. There are some open source efforts also. So what we can have in this AVS is really the ideas of the idea of a committee. You can have, like, for example, we have a scroll multi-prover, right? This scroll multi-prover, the code can actually be run in Intel SGX, Amazon Nitro, and say AMD SCV. And operators from these three different TEs would form a committee, and then they will have to agree on a certain result before this result will be deemed like correct. And again, because of the kind of like low latency, the low overhead that the TE has, the efficiency that the TE has, we are able to actually do this in a very cost-effective manner. And this again raises the bar and make the entire system that much more robust. So yep. And again, all of this is kind of like enabled via the AVS, right? So I'll just kind of go through a kind of quick overview on our multi-prover AVS that we are actually currently running on EigenLayer's mainnet. So you get imagine that there's a few entities here. There's the operators with the different kinds of machines that they operate, like Intel SGX, Nitro Enclave, AMD SCV. Then we have the multi-prover AVS, which is actually what us at Automata we run. There's the attestation layer that I talked about, that I shared with you about, and then there's the AVS contracts that deal with like the TEE committees, the staking, the rewards, stuff like that. And then on the right, you actually see something called reproducible builds. So that is actually something that we are working on also. So this reproducible build is a technique that we use to kind of like defend against supply chain attacks. So you can imagine, like, right? I have a GitHub repo, I open source it, and then I have a binary. Let's say the binary for the TE prover, and I say that this TE prover is built from the SGX GitHub repo that I shared with you just now. The thing is, how do you know that this binary is indeed built, compiled from this GitHub repo? So what reproducible build does is that it makes sure that this process is deterministic, and then we can wrap this whole process in a TE to give that attestation that this binary indeed comes from the source code, the GitHub source code. So the flow of a typical job would be something like, we'll have a multi-proving task that's submitted to the AVS. The operator will actually discover and then register the task, and then it will actually take the binary, like from one of the the library of builds that are reproducible, that are attestable. It will take it, verify that this binary is indeed genuine, is correct. There's no poison in this binary. Load the binary into the enclave, take the task, and then put it into the, take the recipe and put the ingredients into this black box, executes performs the task, like making the cupcake. And then it will take this cupcake and then bring it back to our multi-prover AVS together with an attestation report that everything is okay. And then our multi-prover AVS will, of course, take the attestation report, send it to the attestation layer to make sure that everything is okay. And then this cupcake is is then like sold to the client. In this case, it is like Scroll, right? Because Scroll is the one that will take the cupcake and then say like, yeah, yummy banana cupcake, yay, great. So this is basically what our Multi-Prover AVS architecture is about. So to just kind of like share with you a little bit on some of the stats that we have about 98,000 stakers staking to about 62 different operators with a total of 6.7 billion US dollars worth of restaked ETH that is staked on the AVS. Now, what you can think of it is that all these 98,000 stakers, these 62 operators, and a whole like $6.7 billion worth of ETH is actually used to secure the ZK proof for Scroll currently. Our next version would include linear in the picture also, and we hope to onboard more and more such rollouts. So this kinds of like protect us against like some catastrophic black swan events where proofs fail. But at least we have the corresponding crypto economic stake to actually back this thing. So now the thing about this is, I hope whatever that I've shared would kind of like inspire you, because Multi-Prover AVS is not the only thing that you can do with TEEs. Like what we are running now is a Multi-Prover AVS, but in general, it is a kind of like TEE Coprocessor AVS, right? Like we can have multiple different kinds of service that rely on the guarantees that TEEs provide, and then kind of like form this great service that we can provide to other people. Imagine if you have $6.7 billion worth of crypto economic security. What can you use this amount of security to do? What are some of the things that with the guarantees of privacy and integrity of execution that TEEs provide, can we actually build to make like the entire Web3 ecosystem better, to make the user experience better? So with that kind of thought in mind, we are really very happy to announce that we have this $5,000 bounty together with Encode for the EigenLayer Hackathon. And we are really excited to see like what kinds of ideas and like crazy DApps that you guys can come up with. And really our ask is very simple. It's just two things. One, like I mentioned like less than a minute ago, use cases for possible or future TEE AVS on EigenLayer beyond Multi-Prover. If you can come up with something great, build a prototype out of it, and then do a presentation, share it, and this $5,000 is yours. Or of course, if you can also choose to kind of like do developer tooling or contributions that kind of like support the development and adoption for our Multi-Prover AVS. But I don't know, if I were you, I'm really excited about like the endless possibilities that is enabled by TEEs. So, but anyway, our ask is this two. Like you can do any of the two. So with that out of the way, I just want to share a little bit, like just to kind of like make sure that things are there's clarity on some of like the guidelines. Like I say, what we are looking at is creative ideas that is enabled by TEE. So the kind of like the project that you are hacking on would have to be only possible because of TEEs or certain guarantees that TEEs bring on EigenLayer. So how the way how you can show it to us is by having a kind of like clear description on how TEEs are used to achieve the goals of the project, and how without TEEs this is not possible. Again, like because I'm actually very sure that there's going to be a lot of talented hackers that will be hacking on this thing, right? So in terms of the proof of concept, we will consider like the application based on the kind of like the clarity of the idea, like the pitch, basically, the structure of the proposal, and of course, like if it's technically feasible or not, like is it even possible? Like you have a POC, can we actually make it into a product or a production kind of like ready service that we can include into our AVS even. And finally, like we shared a lot of our tools, we open source a lot of our tools. We believe strongly about open sourcing such that it benefits the whole community. We can kind of like build on each other's ideas and like improve the whole ecosystem. And so one of our requirements would be that any kind of like projects that want to apply for this bounty would have to open source their project under a permissive license, like MIT or Apache 2. So yeah. So there are some helpful links. We have some documentation at docs.ata.network. If you want to read some of the articles that we write, our blog is at blog.ata.network. And finally, our intern, she has been pestering me to like do some shilling for her. So here I am. We have this HackMD kind of like link by our Automata intern. She will actually post some of her musings, some of her like opinions on things on this particular HackMD. Our Automata intern is actually on X, Twitter, to X, and so feel free to follow Automata intern too. So with that, I've actually come to the end of the presentation. Again, I'm so grateful for Encode to actually invite me here to share with you this whole thing. Follow us on Automata. Follow us on X. We are at Automata Network, and that's basically it. If you have any questions, I'll be glad to kind of like take the questions.
Awesome. Thank you so much to Zheng Leong. Such an incredible session there. Lots of different stories and black boxes and talks of fairies. So very engaging for everyone involved. And thank you as well for tackling the questions as we went through the session. I think we've captured everything I can see for now, but of course, as you can see on the slide, to everyone here, please do feel free to reach out to the team on X with any questions you might have there. I'm sure they will be very happy to help. But I guess on that front, given I see no more final questions coming in, I guess that just leaves us to say one more thank you to the Automata team for coming along, also sharing all of the insights into the bounties as well. A little reward for everyone who stayed around. You can get ahead of the game, get started with those. So very exciting time to get involved. Thank you to Automata and Zheng Leong for joining us today. Do you have any final remarks yourself before we wrap things up?
Not really, but like go ahead, imagine like the impossible and start building, start hacking.
Perfect. I think that's the perfect place to wrap things up. So thank you for joining us. We'll see you all again tomorrow. And thank you one final time to Zheng Leong. Thank you.